All right. The next assignment that you've got, homework 9, is posted online. It's got 3 problems, and that assignment is due on Wednesday, the 23rd of March. So you've got a little bit less than 2 weeks for that assignment. In parallel, once we get this feature level thing figured out, you should begin working on phase 2 of your project, which is the optimization process of trying to figure out what's the best pipe size that's appropriate for your network. And that should be uploaded to Blackboard by Friday the 25th. So that's the 2 weeks from today. Today we're going to talk about the application of specific energy ideas and talk about how that allows us to calculate what happens when there's a disturbance to the flow. So remember that Manning's equation can predict the flow depth if you have steady uniform flow, but there's lots of conditions where the flow depth is going to be disturbed by an obstruction like a choke. So remember that this is the specific energy diagram, which is calculating for a variety of different depths and corresponding velocities how much energy there is for one given flow rate. So this curve represents a lot of different depth and velocity combinations, but this is all for one flow rate. And it's for one particular channel geometry as well. You know, it could be a rectangular channel, a trapezoidal, but everywhere on this curve has the same flow rate going through the same channel, just with different slopes, which is causing different depths of flow. What we are going to see is that you can have different slopes that give different specific energies, but there are also other things besides changes in slope that adjust where you're at on this specific energy diagram. One of the concepts that helps us to calculate the new depth downstream when there's an obstruction is the idea that regardless of what the flow depth is, so whether you have a shallow depth and a high velocity or a really deep depth and a low velocity, you have the same flow rate. And what this figure is showing is for a certain specific energy, then the maximum flow rate occurs at the critical depth. So remember, when we looked at the specific energy diagram, the critical depth is the furthest to the left. And that represents the most efficient flow condition. And what I mean by the most efficient is it's conveying the flow rate, this Q, with the least amount of specific energy. And so any depth or velocity combination besides this critical depth requires more specific energy to get that flow rate through the channel. So this is just another graph of that same function, that if you hold the energy constant, then the maximum flow rate that's accommodated by that amount of energy is at the critical depth because it's the most efficient flow depth for a certain amount of specific energy. So another way of looking at the critical flow is it's the maximum flow rate you can get for a certain amount of specific energy, or for a certain discharge Q, it's the minimum amount of specific energy that's required to accommodate that flow rate. All right, so consider, what if you have water flowing through a channel and the water goes through a drop in the bed. What we want to know is, how does that drop downward, the step, change the new depth downstream? Because the specific energy is changed by delta Z. You know, upstream, maybe we had the normal depth, but there was some sort of an irregularity that changed the amount of specific energy that's there. So this is called a drop in the bed. And we want to find out what's the new flow depth 2. And the way that you can do it is, first of all, you diagnose what was the flow condition upstream at location 1. So you could do that by calculating the Froude number or by comparing the flow depth to the critical. So just from inspection, see this dashed line? That's the critical depth. And since the actual depth at 1 is deeper than the critical depth, that means that it's subcritical flow. So if we calculated the Froude number, we'd have a Froude number of less than 1, which would confirm for us that at location 1 conditions are subcritical. And the reason why we want to know that is that after this drop, flow conditions will continue to be subcritical. And we're going to calculate the new depth by using the specific energy diagram. And in the specific energy diagram, which is here, remember there's 2 possible depths. We solved cubic equations in class on Wednesday using the calculator, using Wolfram Alpha. We found out what are the 3 different depths that satisfy that cubic equation. One of them was a negative flow depth, which we just threw out. And then there's 2 other flow depths. One's a subcritical depth, one's a supercritical depth, and we have to know whether we should choose the super or the sub. And the way that you know is that conditions at the upstream location will dictate what are the conditions at the downstream location. Okay, so the way to know what is the new flow depth is you start off with your upstream depth at 1. So you start off with a known Y1. It's measured or just given data, the Y1. It goes over to the specific energy diagram. I'm real proud of these animations, by the way. There's hours of work, literally, to put those arrows in there. I'm just kidding. So it goes over from the depth to the specific energy diagram. And once you know where you're at on the specific energy diagram, it goes down here. You can calculate E1. So you don't have to do it graphically. I mean, you could just use this definition of energy at 1 is the flow depth at 1 plus the velocity at 1 squared divided by 2g. Or sometimes it's more convenient if we express the velocity head in terms of the flow rate q. So y1 plus q squared divided by 2g a at 1 squared. So you find out how much specific energy do you have before the step. And now we're here at E1, and you'll notice that you go to the right for a step down. You're getting more specific energy at 2 because this delta Z is adding energy to the water. And so you can see that on the graphical representation, it's moving it to the right because there's more specific energy. So E2 is however much energy there was at 1 plus delta Z, how big the step was. And then you'd go upward from E2, and there's going to be 2 crossover points, the supercritical root, the subcritical root. And so knowing whether you had super or sub here at location 1 dictates whether you choose the smaller root or the larger of the 2 positive roots. So you choose the new depth at 2 that retains whether it was supercritical or subcritical previously. So the example will work in just a moment, goes through this process of identifying the depth on the specific energy diagram, calculating the amount of specific energy that we have, finding E2, and then solving for the roots for that new energy at 2. All right, so here, let's assume that we have an 8-foot wide channel, and at 1, the depth of flow is 3.5 feet. The water's flowing along, and then it goes down through this step. And the step is a 1.2-foot drop. So then that means that there's going to be more energy at 2. And so what we want to do is we want to find out what is Y2, the unknown depth at the downstream location after the drop. Okay, so let's go through these steps together. Let me turn off the monitor for a second. I'll sketch out We've got a channel that is 8 feet wide. 8 feet wide. And initially, Y1 is 3.5 feet. We've got a flow rate Q is 30 cubic feet per second. And delta Z is 1.2 feet. Okay. So let's find out how much energy there was at location 1. So E1. E1 was Y1 plus Q squared divided by 2G A1 squared. All right, well, what was the area at location 1? So area 1 was 3.5 feet by 8 feet. So if you've got your calculator handy, please follow along and make sure that I've got the right numbers. 3.5 feet times 8 feet, that's 28 feet squared. Okay, so our energy at 1 is going to be the flow depth of 3.5 feet plus the flow rate. All right, plus the flow rate is 30 CFS, so 30 cubic feet per second squared divided by 2 times G, 32.2 feet per second squared, times area at 1 squared, 28 square feet, and square that. Okay. So 30 squared divided by 2 times 32.2 times 28 times 28. Okay, so I got this part of it is pretty minor, 0.017825 feet. Yeah. And then we've got the 3.5 foot depth. So E1 is 3.5 feet plus that. 3.5178 feet. Okay, so that's how much energy there is at 1. The energy at 2, E2, is going to be E1 plus the delta Z. Because it's a step down, it's getting more energy. So this is just showing how we go through the process of calculating the energy at 2. So it's E1 of 3.517 plus 1.2 feet. So E2 is 4.7178 feet. Now, we should calculate the Froude number at 1, just so that we know whether conditions were supercritical or subcritical at the upstream location. Okay, so keep this. I wish we had a bigger board. It's just too small. Froude number at 1. So the Froude number at 1 is Q squared times the top width B divided by G times A cubed, and all of that's to the 1/2 power. Okay, so calculating the top width. Okay, flow rate, so 30 CFS squared. The top width is 8 feet divided by G, 32.2, and then times the area cubed, so 28 square feet cubed. And all of that's to the 1/2 power. So let's do the calculations and find out upstream, was it supercritical versus subcritical? So 30 squared times 8 divided by 32.2, 28 cubed. And then all of that to the 1/2 power. Get 0.10. 0.100. So subcritical. So upstream, let me bring back up the image from before. We could have diagnosed the flow regime at location 1 by calculating the critical depth and comparing our known depth to that, or by calculating the Froude number. What I've done here on the board is I've showed you that the Froude number at location 1 is less than 1, so it's subcritical. The flow conditions at 1 are subcritical. So we need to know that it's subcritical and this new E2, so our E2, those are the two things that we have to know to be able to calculate the new downstream depth at location 2. So let me erase this top part, because we just need to continue the calculations a bit further. Okay, so E2 is Y2 plus Q squared divided by 2G A squared. And instead of A squared, I'm just going to write 8, which is the width, times Y2, and that's squared. Okay, and we know that E2, from what we calculated before, is 4.7178. So 4.7178 is equal to Y2 plus Q squared. So Q was 30 squared divided by 2 times 32.2 for G times 8 times Y2 squared. What's 8 squared? 64? So I'll just write 64 Y2 squared. Okay, let me pause for a moment, and you go through the process of rearranging this to look like a nice cubic equation and then solving for the 3 roots of the cubic equation. So where we're at so far is we know the Froude number at 1 was subcritical. We know E2, and we say E2 is made up of the depth at 2 and the velocity head at 2. Okay, you can see that I've written on the board, it's Y2 cubed minus 4.7178 Y2 squared plus 0.21836 is equal to 0. So let me go to the Wolfram alpha thing and graph that. And we'll find the roots. Y cubed minus, oh, I should have done it in natural language. Y cubed minus 4.7178 Y squared plus 0.21836 is equal to 0. Okay, it graphs it for us. It finds these 3 roots. So a negative root, which is nonsensical and we can throw out, and then 2 positive roots, one which relates to the subcritical depth option and the supercritical depth option. And what these 2 depths have in common is that they both have this much specific energy. They have 4.7178 feet of specific energy. So since we had subcritical conditions beforehand, when we were at the upstream location was sub, then afterwards will also be sub. And so what that tells us is the flow depth after the drop is going to be the larger of those two. It's going to be 4.708 feet. 4.708 feet. Now, my calculations that I had here were a bit different. I started off by calculating the Froude number rather than calculating the E1 first, but point is it was subcritical upstream, and you find out how much energy is there at location 2. And so in that same method, it's 4.708 is the subcritical root. So that will be the new depth. So basically what we're saying is if water goes off this 1.2 foot step, it's not just the same as adding 1.2 feet to this, because it was 4.708. It's pretty close, 4.7, but it won't always be in the linear portion of the specific energy diagram, because what we were doing is, we started off in the subcritical and we went to another subcritical. So remember, from a graphical perspective, what we were doing is we had this amount of specific energy, and because of the step downward, we're moving further to the right. So we want to find out what is the new depth with some additional specific energy where we're moving to the right on that curve. Any questions about the calculations to find out the new depth after a drop down? What do you suppose you'd do if it was a drop up, a step up rather than a drop down?
Subtract.
You'd subtract delta Z rather than add delta Z. That's right. Okay, so let's look at the step upward. If it was subcritical and you're stepping up, then it's going to reduce the flow depth. And this is a little bit counterintuitive. If you think about it, you maybe would expect that because there's this vertical obstruction, maybe you'd think it's going to clog the flow somehow. You'd be forgiven for thinking maybe it would have to flow at a steeper depth over that obstruction. But in fact, what it does is if the conditions are subcritical downstream, the flow will accelerate to get over the obstruction. The velocity is going to be higher at location 2 because the channel width is the same, the flow depth is lower, so that means that velocity has to be higher at location 2. So when you have a step upward and subcritical conditions, what you can think of E1 is the amount of energy that's available to push the water up over this obstruction. So this is how much energy you've got to do the work of flowing downstream and getting up over delta Z. The specific energy at location 2 is going to be, instead of adding the delta Z like we did for the step down, this time you're subtracting the delta Z because there's less specific energy at 2 when the water has to flow up over that obstruction. The total energy doesn't change, but the total energy isn't measured according to the bottom of the channel. But the specific energy does change. Remember that the difference between total energy and specific energy is that total energy is taking into account the velocity head, and so there's more velocity downstream. And also, if you're measuring all of the energy, you're measuring it according to a horizontal datum rather than just according to the channel bottom. So if you use a constant datum for measuring the elevation of the water surface and the velocity head at 1, and that same elevation datum at 2, then that would be the total energy. So stepping up over this obstruction, you've got more elevation in the flow and more velocity, even if the depth is lower. Okay, so think about it graphically. Here's our specific energy diagram. And so you've got a certain amount of energy at 1, and the delta Z moves your specific energy to the left. And so that explains why if you had subcritical conditions initially, why the depth is going to be lower. But if you had supercritical conditions beforehand, then the flow depth would be bigger because you'd be moving from this point on the specific energy diagram to the left. So for subcritical conditions, the new depth would be less for a step up. This is just showing the other case. If you had a step up for supercritical flow, and we can tell that this is supercritical because look at Y1 versus YC. In this case, the Y1 is the actual flow depth, and YC is the critical flow depth. So anytime the actual flow depth is less than the critical, then that's supercritical conditions upstream. And so downstream, it's also still going to be supercritical, but the Y2 is greater than the Y1 was because of the delta Z. So just to step that through the specific energy diagram, we had a certain amount of energy at 1, then shifted to the left for a step up with the delta Z. So less specific energy is moving to the left, and the new elevation, the new depth of the water would be higher than it was at 1 because we're in the supercritical range. All right, so let's practice a step up. We're going to follow basically the same process as before. We have to diagnose the flow regime. And so you've got two ways to do that. You can diagnose the flow regime by using the Froude number, or you can calculate the critical depth and compare the flow at 1 to the critical depth. Does anybody remember what the name of this variable lowercase q is? What did we call that in our earlier lecture on Wednesday? What does the lowercase q refer to?
Flow per unit width.
Good, that's right. Flow per unit width. And so lowercase q is capital Q divided by B. And flow per unit width only really has meaning for a rectangular channel. We wouldn't calculate flow per unit width if you had a trapezoidal channel, unless that trapezoidal channel was very wide. And remember, very wide has a technical definition of being 20 times wider than it is deep. But here, if we want to calculate the lowercase q, it would be the flow rate, which we know to be 250 CFS. So 250 CFS divided by the width of this channel, which is 10 feet. So the lowercase q flow per unit width is 25 feet squared per second. So then once we know that, we can calculate the critical depth y sub c. It's going to be that flow per unit width of 25 feet squared per second. Square that and divided by g, 32.2 feet per second squared. And then all of that to the 1/3 power. Okay? So if you calculate the critical depth, if you got your calculator handy, I think you'll find that that's 2.69 feet. So then we need to be able to diagnose the flow regime at 1 using our known depth of 5 feet and comparing it to YC. So what we'd say is, since Y1 is equal to 5 feet, which is greater than YC is equal to 2.69 feet, then flow at 1 is subcritical. Okay, so we know it's subcritical. And why do we care? It's because we're going to solve a cubic equation that'll have two positive roots, one of which is a subcritical flow depth, one of which is a supercritical flow depth. And we have to know which of those two roots should we choose. Okay, so what I'll do is I'll pause for a moment so you can calculate what is E1, what is E2, and then once you have E2, you find y2 from that. So again, first thing, find E1, then find E2, then calculate y2. Solve the cubic equation.
So if it's subcritical, you choose the larger of the two roots.
That's right.
If it's supercritical, you choose the smaller.
You've got it. So if it's large, if subcritical means slow moving water with a greater depth, supercritical means fast moving water with a shallow depth. So you're right, you'd choose the larger of the two roots in this case because we have subcritical conditions. And I guess not shown on the screen is how do you find E1 and E2? Well, E is y plus q squared divided by 2ga squared. So that is how you can find E1, and then E2 will be E1, I say plus, oh yeah, this equation is right. E2 would be E1 minus the delta Z, because here it's just on the right side. So E2 is going to have less energy because it's a step up. Step up by half a foot. Okay, let me pause for a second and allow you to run the numbers on this. E1 is going to be the 5 feet plus, what I did was I calculated the velocity at 1, so v squared divided by 2g, so it's 5 feet per second squared divided by 2 times 32.2. So the E1 is 5.388 feet. And did other people get that same amount of specific energy at location 1? Okay. So then E2 is going to be E1 minus the delta Z. So the delta Z, in this case, it is a step of 0.5 feet up. Okay, so E2 is 5.388 feet minus 0.5, so that is 4.888 feet. So that's how much specific energy there is at 2, and so then the specific energy function for 2 is 4.888 feet is equal to the flow depth y2 plus q squared divided by 2ga squared. So q squared is 250 squared divided by 2 times 32.2. And then a squared, since this is a 10-foot wide channel, it's 10 times y2, and that's squared. And let me erase the top part of this so that we'll have some room to continue. All right, so it is, if we rearrange it, 4.888 is equal to y2 plus 9.705 divided by y2 squared. Okay, and then further rearrange that. It's y2 cubed minus 4.888 y2 squared plus 9.705 is equal to 0. And then the roots, it's going to have negative 1.26, 1.762, and 4.388. 383. And of those, we choose the larger because the flow upstream was subcritical, the flow downstream will be subcritical. So it's going from an earlier flow depth of 5 feet, and its flow depth is going to be reduced. It's going to be reduced to 4.38. So it's not just as simple as subtracting out the step. You know, the step height was half a foot. So the initial flow depth was 5 feet. If all we did was subtract half a foot, that would suggest it's 4.5 feet. But actually it goes even shallower than that. It goes to 4.38 feet as the new flow depth because the velocity head is changing as well. It's not just the depth that's changing. You lose half a foot of specific energy. Some of that is going to be depth, some of it is velocity. Yeah?
Would there be able to be a step that could change the characteristic from subcritical to supercritical?
Good question. Yeah. There's a maximum step height that can be tolerated. And if the step height is too big, then it will cause pooling upstream. And so one of the things that we'll do after spring break is talk about what's the maximum delta Z that the water has enough energy to get over. So you could say that if you have critical flow conditions at 2, so set y, the depth downstream to the critical depth, then you can solve for the delta Z max. And then any delta Z bigger than the delta Z max basically is going to cause the depth at 1 to get even deeper so that it can accumulate enough energy to get over that larger delta Z. That's a great question. Just a reminder that when you have a rectangular channel, you can calculate the critical depth with this formula. Under other conditions like a non-rectangular channel, you could use this. But when you have critical flow, the depth represents 2/3 of the specific energy. So it's kind of convenient to, we won't do this last example, but if you have critical flow conditions, you can find the specific energy by just multiplying the critical depth by 3/2. And then that'll give you the specific energy. All right, well that's it for today. Hope that you have a nice spring break. And stay tuned because I'll give you some follow-up information on how to activate more pipes for Bentley. Take care.